Today, we're going to break down the recipe for rain. Seriously, we're going to follow the journey of water from this invisible gas that's all around us to a full-on downpour. So let's jump right in.
I mean, it's a question we've all probably asked as a kid, right? It seems so simple, but the answer is this incredible mix of physics and chemistry happening miles above our heads. So, where does it all even begin?
While the first and most important ingredient in our recipe is water, but not the water you can see in a lake or an ocean. We're talking about the water that's always in the air around us, as a gas. You know it as humidity. Okay, so first, let's get a handle on absolute humidity. This one is actually super straightforward. It's just the actual amount of water vapor hanging out in a specific chunk of air. That's it. How many grams of water in 1 cubic meter of air? Simple.
But this is where it gets interesting. Relative humidity is a different beast because the air's ability to hold water changes with temperature. Think of warm air as a giant sponge that can soak up a ton of water. Cold air? It's like a tiny, less absorbent sponge. So relative humidity tells us how full that sponge is as a percentage at its current temperature.
So here's the key difference, right? Absolute humidity is the raw number, how much water is literally there. Relative humidity is about how full the air feels. This is exactly why a cold winter day with high relative humidity can feel so damp and chilly, even though the absolute amount of water in the air is way lower than on a hot, so-called dry summer day. It's all relative to the temperature.
And that brings us to the dew point. You can think of this as the magic number. It's the critical tipping point, the exact temperature the air has to cool down to before it hits 100% relative humidity. Once the air hits its dew point, it is completely saturated. It literally cannot hold one more molecule of water vapor. And at that moment, the invisible is about to become very, very visible. Okay, so we've got our invisible water, and we know we need to cool it down to its dew point. Now we need the action, the processes that make it all happen. And in the atmosphere, this is basically a constant tug of war between two opposing forces. Evaporation and condensation. One adds moisture to the air, the other takes it away. Evaporation, fueled by heat, turns liquid water from oceans and lakes into a gas that rises up. Condensation is the total opposite. It's caused by cooling, which forces that water vapor to turn back into liquid water. This back and forth is the engine that drives our weather.
But here's a crucial little secret. Water vapor can't just decide to become liquid on its own in midair. It's too small, too scattered. It needs a little something to grab onto. And that something is tiny, microscopic particles of dust, salt from the ocean, or even smoke. Without these invisible little specks acting as seeds, you wouldn't get clouds or rain. No way. So now we've got our main ingredient, water vapor, and we have our process, condensation. Now we finally get to see the results. This is the part of the recipe where our invisible ingredient makes its grand entrance.
You see this stuff all the time. On a cool, clear night, the grass gets cold. Once it cools to the dew point, boom, condensation happens right on the blades, and you get dew. If that dew point happens to be below freezing, you get frost instead. And if a whole layer of air right near the ground cools to its dew point, you get fog, which is, for all intents and purposes, just a cloud that's sitting on the ground.
Now, as cool as dew and fog are, the real action, the main event for our recipe for rain, happens thousands and thousands of feet up in the atmosphere. We are talking, of course, about clouds.
And there are a few main types. Way, way up high, you get the thin, wispy cirrus clouds, which are actually made of tiny ice crystals. In the middle altitudes, you have the classic puffy cumulus clouds, the cotton ball ones you see on a nice day. Lower down, stratus clouds form in big, gray sheets that can cover the whole sky. And then you have the nimbus clouds. Their name literally means rain in Latin, and they are the dark, heavy, shapeless clouds that mean business. All right, so we've collected the water, we've condensed it into a cloud. Now it's time for the grand finale. This is the final step where all that moisture gets released and sent right back down to Earth. The process, of course, is called precipitation. So what's happening is that inside that cloud, all those tiny water droplets that formed on the dust particles are bumping into each other, merging and growing bigger and heavier. Eventually, they get so heavy that the air currents inside the cloud just can't hold them up anymore. Gravity wins. And precipitation comes in a few different flavors. The most common, obviously, is rainfall. But if it's below freezing inside that cloud, the water vapor forms directly into these beautiful hexagonal ice crystals we call snow. Sleet and hail are a bit more complicated. They involve some wild journeys through different temperature layers. Let's just take a look at the wild ride that a piece of sleet goes on. It starts its life as a regular old raindrop falling out of a warmer layer of air, but on its way down, it hits a roadblock, a thick layer of air that is below freezing. As it falls through that cold zone, the raindrop freezes solid into a tiny ice pellet just before it hits the ground. And that, my friends, is sleet.
So you see, the basic recipe for rain is the same everywhere, but the final dish can turn out completely different depending on the kitchen. And in this case, the kitchen is the local geography. The landscape itself can totally change the weather.
Let's look at two major types. Convectional rain is all about raw heat. Think of a scorching summer afternoon. The sun bakes the ground, and that hot ground heats up a pocket of moist air, which then shoots upwards like a hot air balloon. As it rockets up, it cools fast, condenses, and dumps all its water in a sudden, intense thunderstorm. But orographic rain is different. It's caused by terrain. When a big mass of moist air blows in from the ocean and slams into a mountain range, it has nowhere to go but up. It's forced to climb, it cools down, and all that water gets squeezed out like a sponge, causing tons of rain on one side of the mountain.
So what happens after that air has dumped all its rain? Well, it keeps going over the top of the mountain. As it slides down the other side, the leeward side, it warms back up and becomes incredibly dry. This creates a phenomenon known as a rain shadow.
So there you have it, the complete recipe for rain, from invisible humidity all the way to a raging storm. And that brings us to a final thought. That process we just talked about, orographic rain creating a rain shadow, that is precisely why you can have a lush, green, vibrant rainforest on one side of a mountain and a bone-dry, arid desert on the other. It's the same air, the same latitude, but two completely different worlds. It just goes to show you, while the recipe for rain might be universal, geography is the ultimate chef.